Today we are covering Chapter 3, Review Questions from Berean Builders Discovering Design with Chemistry. So, as before, I'm not going to cover these definition questions because those are easily found in the book. I'm also not going to cover question 2 or question 3 because those are quite easily found on the very first page of this chapter. And essentially, these are definition questions also. Question 4, though. Suppose someone throws a rock through a window. At the moment of impact, indicate the forces involved in the situation, besides the gravitational force and air resistance. Indicate the consequence of each force. Okay, I'm not going to write this answer down because this is just purely a writing question and not doing any calculations for you. But essentially, what is happening? So we're ignoring gravity and any air resistance for this question. And so we know a rock is being thrown at a window, and that window and the rock do impact each other. So that rock is going to exert a force on the window, of course. And the consequence of that force, well, likely the window will break. And so the rock exerts a force on the window, causing the window to break. Then, because of Newton's third law, we know that there has to be an equal and opposite reaction. And so that window then is going to exert an equal but opposite force on the rock. And the consequence of that is when it exerts that force on the rock, it's going to cause that rock to slow down. It's not going to be going at the same speed after it hits that window as when it started. Now we'll move on to question 5. When someone fires a gun, the gun pushes back against that person. This is often referred to as the gun's kick. Explain why a gun does this using Newton's third law. Again, this is just an explanation question, so I'm not going to write it down, but I will give you the explanation. So the gun obviously exerts a force on that bullet, causing that bullet to exit the chamber away from the gun. And also, we could say moving forward, okay? At the same time, though, that bullet, because of Newton's third law, is going to exert an equal but opposite force on the gun. And that is going to cause the gun to do the kick backwards. Okay, so now let's do our first calculation problem here. A 72 kilogram person is standing on a floor. What is the strength of the normal force and its direction? What is exerting the normal force? What happens if the thing exerting the normal force isn't strong enough to exert that force? Okay, so I'm just going to take what I know here and start writing things down. I'm given a mass, so M equals 72 kilograms. Okay, and that's pretty much all that I am given. Okay, I know I'm probably going to use gravity in here, but this is the only other thing that is given outright to us. And so now I need to decide what formula I can use to solve this problem. And the formula I'm going to use isn't one that is given as an equation, that like a listed equation in the book, but I do want to point it out because when I'm reading through the book, I'm also looking for equations that are used that might not be listed as equation 3.1 or something like that. And so a great place for that is in the examples in the book. And in the example that asks a similar question in this chapter, it gave us this equation here, right? The net force when we are dealing with gravity situations, it is equal to the normal force plus the weight, okay? And we know from chapter 2 that weight equals the mass times the acceleration due to gravity, okay? We also kind of know and we've already have used this equation before in chapter 2, but force is also equal, and we're calling it net force, but it's still force, equal to the mass times the acceleration. Okay. So this is what I am going to use here, okay? And I need normal force. That is what this question is asking for, right? And I'm given a weight, and whenever we are dealing with just the weight of something by itself, that net force is 0, right? There's no other acceleration that is going on, and so this net force is 0. So that's kind of given to us, but we have to use the clues in the type of problem that it is, okay? So the formula I'm using is F net equals the normal force plus the weight, okay? I know the net force is 0. I'm going to be solving for this normal force, and the weight is we're going to use the mass to determine that, right? So weight equals mass times the acceleration due to gravity. So it's going to be 72 kilograms times negative 9.81 meters per second squared. And if you don't have the numbers for gravity, whether it is feet per second squared or meters per second squared, you should really be working on memorizing these, because gravity is going to come in over and over again. And so these are numbers that you should just know right off the top of your head. Negative 9.81 meters per second squared and negative 32.2 feet per second squared. Okay, so now I can solve for the normal force. And so this weight is, when you multiply this, you're going to get 706 newtons. So kilograms times meters per second squared is Newton, the unit for newtons. But we need to make that into two significant figures because of the 72 kilograms. And so that 706 newtons is going to round to 710 newtons. And it's negative because we are dealing with gravity here. And when we have this net force, right, that needs to equal 0, well, it equals 0 because one of these is positive and one of these is negative. Okay. Okay, and so our normal force equals 710 positive newtons. And so that is the force that is being exerted by the floor pushing up on the person that is standing on the floor. That is the equal but opposite reaction from the floor. Okay, so starting to write out this answer, the normal force is 710 newtons pushing up. Okay, So if you remember why I highlighted this, this is a vector quantity. And so I have to have a direction along with this. So like this normal force would also be a vector quantity in this particular problem. Okay, so 710 newtons pushing up. So we've answered 2 of the questions. What is the strength of the normal force and its direction? And we haven't, well, I talked about the other answer, but what is exerting the normal floor, the normal force? The floor is exerting the force. Okay, and then what happens if the thing exerting the normal force isn't strong enough to exert that force? Well, what would happen is that if the floor is not strong enough, the person will fall through the floor. All right, now question 7. A man is standing on a scale in an elevator. When the elevator is at rest, it reads 156 pounds. When the elevator accelerates upwards, it reads 162 pounds. What is the acceleration of the elevator, and what will the scale read when the elevator is traveling up with a constant velocity of 26 feet per second? Okay, so let's go ahead and see what we need to highlight and write things down. Okay, so what are our vectors in here? Okay, so we're going to use the a similar equation from before, the same one, that force net equals the normal force plus the weight. We don't have force net or normal force in here, but we just kind of know that we're going to need to use those. So I'll highlight those when we get to that. Okay. We do see upward, so we're gonna, define upward as positive. That's what makes sense, right? And now let's go ahead and write out what we know and then start working on the equations, okay? So we have a weight, and that equals 156 pounds. That is the weight of the man at 0 acceleration. So that is his normal weight, okay? Our normal force, so what our normal force is going to be when we are accelerating upward, and that's going to equal 162 pounds, okay? All right, and so we have this net force equals the normal force plus weight, right? And so our net force equals 162 pounds plus our weight. And our weight, because this 162 pounds is when we are, it's the force that is pushing upward, the weight is pushing downward, okay? And so in this case, our weight is going to be a negative 156 pounds, okay? So the weight is pushing down, this normal force is pushing up. And so this one has a negative and this one is a positive, okay? So then that net force then is going to be 6 pounds, okay? But that's not what the question is asking for. It's asking for what is the acceleration, okay? And we know that force is mass times acceleration, okay? And so now we're going to break down this net force into mass and acceleration, okay? So our 6 pounds equals our mass times acceleration. Now, how do we get this mass? Well, we're going to have to backtrack and get our mass from the weight, okay? So I'm going to come just over here and do that real quick. So remember, weight equals mass times gravity, okay? And so our weight, our mass is unknown, but our weight is 156 pounds. And remember that the English units for weight is pounds, but pounds comes from slugs times feet per second squared, okay? So equals the mass times, I'm running out of room here, but 32.2 feet per second squared, okay? So I'm going to divide both sides by the gravity here. So divided by 32.2 feet per second squared, right? The feet per second squared cancel, and you're going to end up with slugs. And so when I do that, 156 divided by 32.2, the mass is going to be 4.84 slugs equals the mass. Okay, and so now I can plug that into here. 4.84 slugs times the acceleration, okay? And so now I'll divide both sides by the 4.84 slugs. And so just remember that this pounds, I can restate using those same units. So 6 pounds would be the same as 6 slugs times feet per second squared, right? And so the slugs will cancel, and we're going to be left with feet per second squared when we do this calculation. Okay, so 6 divided by 4.84, I'm going to round whatever answer I get to just one significant figure, because that's all I have with the 6, and so that's the max I can use. And so what I'm going to end up with 1 foot per second squared equals the acceleration. And so this is my answer. Okay, so writing that out, the acceleration of the elevator is 1 foot per second squared. Okay, so let's look back at what this question is asking for. Okay, first is what the acceleration of the elevator. Okay, and you know what I should have done? I didn't even notice it. Acceleration, vector quantity, right? And so do I have a direction? I do not, right? And so I need to fix that. The acceleration of the elevator is 1 foot per second squared. The question did already say that it is moving upward, but we still need to put it in here, okay? So the acceleration of the elevator is 1 foot per second up. And then what will the scale read when the elevator is traveling up with a constant velocity of 26 feet per second, okay? So if velocity is constant, that means the acceleration is 0. And the only way that we get a net force that is not 0 is if the acceleration is not 0. At any point when the acceleration is 0, this normal force is going to be equal and opposite of the weight. Okay? And so our answer for the second part is that when the velocity is constant and acceleration is 0, the scale is going to read the normal weight of the man, which is 156 pounds. Okay? So the scale will read 156 pounds at any constant velocity. So the number there doesn't even matter. Okay, it's kind of thrown in there to throw you off. This 26 feet per second, you don't need it. Okay, it doesn't matter what that constant velocity is. If it's constant, the acceleration is 0, and the scale is going to read just the weight of the person. Okay, question 8. A 112 gram object is sitting at rest on a table. It takes a force just greater than 0.512 newtons to get it moving, and it takes a 0.345 newton force to keep it moving at a constant velocity. What are the coefficients of static and kinetic friction? Okay. So looking for any vector quantities, this is going to fit with my equation 3.1, which I've called, just based on the description before that equation, the relation between normal force and force that is due to friction. Okay. And we are specifically told that this relationship is not a vector quantity. It is just the relationship between the two. Okay. So we don't have any highlighting to do here. We do want to go ahead and write what we know. Okay. So our mass is 112 grams. Knowing what I know at this point about everything we've done so far in physics, I'm going to need to convert this. Okay. As soon as I see grams, I'm like, okay, everything we've done so far, we're working in kilograms. So let's go ahead and just convert that now. And it's nice that gram to kilogram conversion is so easy. Just move that decimal place. Okay. It takes a force greater than 0.512 newtons to get it moving, and 3.345 newton force to keep it moving. Okay. And then it asks, what are the coefficients of static and kinetic friction? Okay. So the equations that we're going to use, I want to refer to this first before I write any more of these down. Okay. Is this, right? So lowercase f is the force due to friction, and that is what we're being given here. Okay. The force to get it moving and to keep it moving. Those are both forces due to friction, and they go with different coefficients, right? So, the mu s is the coefficient of static friction, and mu k is the coefficient of kinetic friction, okay? And we know that static friction is always the higher number, okay? So let's do the static one first, okay? So static means it is not moving, and within that formula, you are determining how much force it takes to get it to start moving, okay? So that's going to be I'm going to put an FS here just so I know which one they go with. 0.512, right? And then we have I'm going to call it FK equals 0.345, and those are both newtons. Okay, so now plugging this in, Fs equals mu times the normal force. Okay. let's plug in what we know here. So Fs is 0.512 newtons. Okay, my mu, and this is going to be a mu s, right? We don't know yet. Okay, that's what we are being asked for. My normal force is going to be simply my weight. Okay, the opposite of weight, right? So it's going to be my mass times gravity. And so we're going to multiply 0.112 kilograms times, and then we don't need to put a negative here. It's just going to be gravity. And in fact, the normal force would be the force pushing up, so positive is fine. So 9.81 meters per second squared. Okay, and so to get my static coefficient of friction, I'm going to divide both sides. Okay, and remember, newtons equals kilograms times meters per second squared. So I'm going to divide by this. It's the same units, okay? And so they'll cancel out. 112 kilograms and okay, and when I do that division, I'm going to get 0.466 is my static coefficient coefficient of static friction. Okay, so that's the static, and now I'm just going to do the same thing and get the kinetic. Okay, so for the kinetic, I have Fk equals my mu k times the normal force. And so my Fk is 0.345 newtons equals mu k times, it's the same numbers for this normal force, 112 kilograms, 9.81 meters per second squared. Divide both sides by that. Okay, and so for the coefficient of kinetic friction, I'm going to get 0.314. Okay, and remember that these don't have units with them. Okay, so newtons is kilograms times meters per second squared. All of that just completely cancels. Okay, and you're left with no units for the coefficients of friction. So my final answer is the coefficient of static friction is 0.466, and the coefficient of kinetic friction is 0.314. Okay, now question 9. A force of 451 newtons west is applied to a 125 kilograms box that is at rest. Will it move? And if it does move and that same force continues to be exerted, what will be its acceleration? The coefficients of friction are 0.35 and 0.21. Okay, so I have a force that is going in a direction, okay, and I'm going to assign west positive, and I need to know what its acceleration is. So I've highlighted my vector quantities in the equation that are going to help me remember to include direction in my answer and as I'm working the problem. And now let's write what we know. So we have a force that is exerted on this box, and that is 451 newtons, okay? The newtons west, I'm assigning west to be positive, so I'm just going to say 451 newtons, okay? My mass equals 125 kilograms. I have two coefficients of friction. The static coefficient of static friction is going to be the bigger one. So my mu s equals 0.35, and the smaller number, 0.21, will be my coefficient of kinetic friction. Okay. So first, we need to know, will this box move with this force that is applied to it? Okay, so let's use our equation that is for force and friction. So my force equals my mu. We're going to do the static first to see if the box will move from rest times my normal force, okay? So F equals 0.35, and we are multiplying this times 125 kilograms, and then the acceleration due to gravity, 9.81 meters per second squared. Okay, so when I multiply all that out, and then I'm going to get 429 newtons, but I'm going to round it to get just two significant figures because I have this coefficient of static friction that is 0.35. So 430 newtons is going to be the force required to move the box from rest. Okay, so the force that has been applied is 451 newtons, and so the answer to this first part is yes. Yes, the box will move. Okay, but I'm not done yet. There's a lot left to read, right? If it does move and that same force continues to be exerted, what will be its acceleration? Okay. So now we need to determine what the force that is required to continue moving this box based on the coefficient of kinetic friction. Okay. So for here, we're going to use the same formula as this. It's just I'm using mu k. I'm not going to write this whole, actually I will. So F equals mu k times the normal force again. Okay, so F equals 0.21 this time. And again, 125 kilograms and 9.81 meters per second squared. So when I multiply all these out, I'm going to get 258, but that's going to be needing to be rounded to the nearest two significant figures. And so that answer for the force required to continue moving the box is going to be 260 newtons. Okay, but that doesn't answer the question yet because I'm still needing the acceleration. And this is not acceleration, this is just force. So I'm going to use my net force equation. And with this, it's going to be determining the force that is being applied and what is the opposite reaction of force that is coming from the friction. And so then therefore, what is the net force that has overcome that kinetic force required due to kinetic friction. Okay, so I have 451 newtons that is being applied, and my opposite force, this is 451 newtons pushing west. This force, this kinetic force, is pushing east, is pushing the opposite direction. Okay, and so I'm going to be subtracting it, 260 newtons, and with that, I'm going to get, you would get 191, but we need to be significant figures to the least precise digit. Okay, and remember this 260 newtons was just two significant figures. And so it's going to round to 190 newtons is my net force that has been applied to the box. So now I'm still not answering this question, right? But now that I have a net force, I can use it to determine what the acceleration is upon, or that the box is undergoing, okay? So here I'm using force equals mass times acceleration. And so my force is 190 newtons. Or you can rewrite this because we're going to be going into mass and acceleration units. Kilograms times meters per second squared equals, our mass is 125 kilograms. And our acceleration is our unknown. Okay, we're not dealing with gravity in this part of the equation. We're dealing with east-west direction and that acceleration. We've already accounted for all of the gravity and the friction that is due to gravity. Okay, so the kilograms are going to cancel. Sometimes it's easier to cancel before you even do the division. It's easier to see how things cancel. So divided by 125. And so with that, with the calculator answer, you're going to get 1.52. We need to get this to two significant digits because of this 190. And so our acceleration is going to be 1.5 meters per second squared equals the acceleration. Okay, so now we can go back to this question. If it does move and that same force continues to be exerted, what will be its acceleration? The acceleration will be 1.5 meters per second squared, and acceleration is a vector quantity. We are positive, we're moving west. And make sure that that makes sense, right? It's the force is pushing it west. So that is, and we know the force was more than needed, so it's gonna go west. So let's double check, make sure that we have answered all of the question. Will it move? Yes, the box will move. If it does move and that force continues to be exerted, what will be its acceleration? Acceleration will be 1.5 meters per second squared west. And this part is not a question, it was just extra information given to us. So that is our answer for 9. So now let's do question 10. A 24.3 kilogram box is being pushed across a floor. It starts from rest and takes 2.20 seconds to travel 5.00 meters. What force is being used to push it? And it tells us the coefficients of friction are 0.39 and 0.22. So the first thing I'm going to do is see if there are any vector quantities that I need to be paying attention to. And of course, force is a vector quantity. There's nothing in here that gives me much in the sense of direction other than across the floor. Okay. And so that is my only direction, but that is in fact a direction. So across the floor is going to be defined as our positive value, or positive direction, I should say. So now we will just go through the variables and see what we have and look at what we need. Okay, so first variable we're given is 24.3 kilogram box. So my mass is 24.3 kilograms. We know that it starts from rest. Okay, so whenever we see the word rest, we are thinking velocity is 0. That should be the first thing that pops in your head. Okay, and so it's starting from rest. And so my velocity naught equals 0 meters per second. It's going to take 2.20 seconds to travel. So I have a time, t equals 2.20 seconds. And it's going 5.00 meters. So that is my delta x, my displacement, 5.00 meters. Okay, then I have my question, what force is being used to push it? And then we're given one more piece of information. Coefficients of friction are 0.39 and 0.22. A lot of these questions, we haven't noticed yet, we are given two different coefficients of friction. We're not told which is which, but by this point we definitely should know that static is going to be the bigger one and kinetic will be the smaller one. And so we don't necessarily need both of these. If we just look at what this question involves, there's movement here, right? It's not asking us how much force it takes to get it from that stop position. We are measuring from the very moment it starts moving from rest until it stops. Okay, so we will be using the kinetic coefficient, okay? And we can ignore the static here because that does not pertain to this problem, okay? So I'm going to go ahead and write that down, that mu kinetic is 0.22. And remember, those coefficients have no units associated with them. Okay, so now I have all of the variables that I've been given, and I'm going to look at what I have and what I still need. Okay, so my question is what force is being used to push it. Okay, a lot of times with these problems, it helps to know what your final equation is going to be. This is going to be a multi-step equation problem, but if we know what our final equation is going to be, what equation we ultimately need to use to get force, then we can kind of backtrack and figure out, okay, what are we missing in that equation in order for us to figure out the answer. Okay, so I'm going to go ahead and write down what that final equation is going to be. Okay, so it's what force is being used to push it. And I'll tell you that this is not an equation that was written as an equation with a number in the chapter, but it's one that through the example problems and the and the other problems in the book, you kind of really gather that, okay, this is used a lot, okay? And so whenever I'm seeing that, when I'm taking notes, I'm including that as part of my equations. And so when I have these stars on my notes, that means it wasn't an equation with a number that, is in a pink box in the book, but it's really one that I think I need to know, okay? And so this one is actually, it's kind of an adaptation of this one. Okay, it's an equation for net force, but there's different things going on. All right, this one is just pure gravity happening, but this is when there's that friction. Okay, and so my net force is whatever force that has been used to push or pull an object, plus that force due to friction, which we previously got from equation 3.1. Okay. I also put myself a note here. It's great. Like within your notes, give yourself more notes. That this F number is always going to be negative because gravity is negative. All right. And this force due to friction is acting against this force that is pushing or pulling the object. Okay. And then you get the net force from that from the relationship between those two forces. Okay. And so that is what ultimately I'm going to end up needing to use in this equation, in this question 10. So my net force is equal to the force of pushing plus F. Okay. So ultimately, I'm going to be using this equation. Now, what I need to find out, of course, is the force of pushing. And so what am I missing in my F and my F net? All right. So my force due to friction is simply my coefficient of kinetic friction times my mass times gravity. So I have everything for that, but I don't have everything I need for the net force, all right? Because for the net force, of course, I need the mass times the acceleration. And I don't have acceleration spelled out here, right? I have the mass for net force, but I don't have acceleration, okay? And so that is how my thought process is to get started. Ultimately, I'm going to need this equation, but I need to get this net force first. Okay, what do I use to calculate that? Mass times acceleration. Oh, I have mass. I don't have acceleration. Do I have enough information to figure out the acceleration? And the answer to that is yes, I absolutely do. Okay. So for the acceleration, we're going to be pulling from one of the equations from chapter 2 that we have previously memorized. And these equations are kind of come into play a lot. So these equations, they're really ones that we just need to know forwards, backwards. It needs to immediately be something popping in your head. So if you haven't been working on that, you should be all of these acceleration equations. Okay. So we have initial velocity, we have time, and we have displacement. Okay. We don't have final velocity. So there were two displacement equations from chapter 2. One of them uses final velocity squared equals the initial velocity plus 2 times the acceleration times the displacement, right? And what we are missing from that is the final velocity. So we can't use that equation. And instead, we're going to use that second equation, equation 2.16, which is delta x, our displacement, equals our initial velocity times time plus 1/2 of acceleration times time squared. Now we don't have acceleration, but we have every single other part of this equation, and so we can determine acceleration with this equation, okay? So my delta x is 5.00 meters, Okay, my initial velocity times time, that's just going to be 0, right? Because my initial velocity is 0, and it doesn't even matter what my time is at that point, right? So I'm just going to put a 0 here. I'm not going to say 0 times 2.2 seconds, right? We can just put 0. Plus 1/2 times my acceleration and time squared. So we're going to have 2.20 seconds, and we will be squaring that, okay? So solving for acceleration, just don't worry about that 0 plus, right? And so divided by 2.20 seconds, sorry, I'm getting ahead of myself, divided by 0.5 times 2.20 seconds squared, right? So all of that goes under there. Okay, and with that, I'm going to get 2.07 meters per second squared equals the acceleration. Okay, so that is acceleration. Now I'm still not yet to my net force. I need to use acceleration to calculate the net force. Okay, so like what is actually happening, like the actual acceleration across the floor, that is the net force. That's the ultimate result of the combination of that force being pushed and the force due to friction. Okay, so now I'm going to use force equals mass times acceleration to get my net force. And so that's going to equal 24.3 kilograms times 2.07 meters per second squared. And with that, I'm going to get 50.3 newtons. Okay, so 3 significant figures here. So now I can plug into here. So my net force is 50.3 newtons equals this force of pushing plus my force due to friction, which I'm going to use the coefficient of kinetic friction, 0.22, times my mass, 24.3 kilograms, times my times gravity, 9.81 meters per second squared. Ran out of room here. Okay. And so with that, I'm going to get 50.3 newtons equals that pushing force plus, and that actually, I messed up here. So this force is always negative, right? That, remember my note that I pointed out? Okay, so that's going to be a subtraction. Okay, and so all of this, it needs to be 2 significant figures because my coefficient of kinetic friction only has 2 significant figures. And so when I calculate all this and then round to 2 significant figures, I get 52 newtons. Okay, so now I'm going to add 52 newtons to both sides to solve for this pushing force. And when I add these with significant figures, I am only adding to the least precise significant figure. All right, so this only goes to the ones digits. This goes to the tenths. So this is the less precise one. So I'm going to go to the ones place. So my answer here is going to be 102 newtons equals the force of pushing. Okay, and so my final answer then is 102 newtons of force is used to push the box across the floor. Now, when I check this, okay, I had a vector quantity. Do I have anything that needs to have, and the vector quantity needs to be applied to the question that was being asked, right? And so am I applying a direction here? And the answer is yes, right? I'm saying it's being pushed across the floor, okay? We didn't have an east-west, but across the floor is our direction that we were given for this problem. So as long as you have across the floor somewhere, you could say 100 newtons of force across the floor is used. That would work fine too. Okay. Now question 11. A 95.0 kilogram box is being pushed across the floor. We have across the floor again, with a constant force of 195 newtons. It has an initial velocity of 2.6 meters per second north. How far will it travel before coming to a rest? The coefficients of friction are 0.320 and 0.230. Okay, so I am seeing across the floor again. That is a direction. I have initial velocity, and then I also have a direction here that says north. Okay, so here I'm getting a little bit more specific. Across the floor equals north in this case. Okay, north is our positive. And then it says, how far will it travel before coming to a rest? So this question, how far will it travel? There's no direction associated with it. It's not saying what is the displacement. So we may use these vector quantities as far as determining signs, but we're not going to need it in our answer. So now let's go ahead and look at what variables were given. So we have 95 kilograms, so we have a mass variable. I have a constant force of 195 newtons, that's pushing. So this is my F push equals 195 newtons. I have an initial velocity, so V naught equals 2.6 meters per second. And I'm not going to write north here because north is just positive. And then I have coefficients of friction. Okay, so again, I'm going to look, am I determining any kind of force that's being used to start that movement from rest? No, that initial velocity is already moving. So we're definitely going to be using the kinetic friction coefficient. So my mu k equals 0.230. Okay. So here I am given the force of pushing and I'm given everything I need to determine the force due to friction. And so really a good place to start is probably going to be what that net force is, so I can determine things that are due to the acceleration. Okay, so net force is a force due to pushing minus, and you know, when I write this equation, I on my equation sheet I put plus, but you know, you can just put minus. Just give yourself a reminder that it's always this is always gonna be negative, because this is an opposite force than the force due to pushing. Okay, so we're given a nice easy number for the force due to pushing, just given that number, minus my coefficient of friction, 0.230, times my mass, 95.0 kilograms, times gravity, 9.81, meters per second squared. Okay, and so when I calculate all that out, I have 3 significant figures in all 3 of these values. So whatever I get here, I will round to 3 significant figures. And this is going to be 214 newtons. And so my net force then is negative 19 newtons. Okay, and that makes sense, right? Always looking like, okay, does the number I got make sense? So that initial velocity is 2.6 meters per second, and then it's coming to rest. So yes, the force is, the acceleration is negative. It's going from a positive value to a 0 value, so that force should also be negative as well. Okay, so we're on a good track there. So now I need to determine the acceleration. Okay, so force equals mass times acceleration, right? So I can use this here, negative 19 newtons equals my mass, 95 kilograms, times acceleration. So I'm going to determine acceleration from this. And so when I divide by 95.0 kilograms, move this up here. Okay, and so my acceleration then is going to be negative 0.20 meters per second squared. So I had 3 significant figures here, but I only had 2 on the force. Okay, and so I have to limit this to 2 significant figures. And so whatever this is, which it actually turns out to exactly negative 0.2, but put this 0 here because you actually have 2 significant figures, and and you need to carry that forward through the rest of the problem. Okay, so this is my acceleration. Okay, but we are still not done because we need to figure out how far it's going to travel before coming to a rest. All right, so we're determining a displacement value. Okay, so this gives us, remember there's 2 displacement equations with acceleration, and so one of them includes the final velocity, and the other one does not. And you know what I just realized is I did not include a final velocity here, but we're given that information, right? Sometimes it's sneaky, and I told you this in the last problem, and then I forgot to look for it myself. When you hear that word or see that word rest, there's a velocity associated with that, right? So actually we had one more variable that we were given, and that's that final velocity equals 0 meters per second. Okay, so if we remember the 2 problems that have to do with displacement and acceleration, the first one is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Okay, we have all of those things: final velocity, initial velocity, acceleration, and then we can use that to determine displacement. We're missing just that one variable. The other one is displacement equals initial velocity times time plus 1/2 acceleration times time squared. We're given no information about the time here, so that one does not help us. Okay, so we're going to use that first one. Final velocity squared equals the initial velocity squared plus 2 times the acceleration times the delta x. Okay, so my final velocity is 0, and if we square it, it's still 0, so I'm just going to write 0. Initial velocity, 2.6 meters per second. Don't forget to square it, plus 2 times my acceleration, negative 0.20 meters per second squared times delta x is my unknown. Okay. So now I'm just going to go ahead and do this calculation and move it over at the same time. Okay, so when I do this 2.6 squared, I get 6.8, and when I move it over to the other side of the equation, then it's going to be negative. And so I get negative 6.8 meters squared per second squared equals negative 0.40. So that's what this is, multiplied meters per second squared times delta x, right? And then to get delta x isolated, divide this both sides by negative 0.40 meters per second squared. Okay, so one of my meters is going to cancel, right? And the second square is going to cancel, and I'm going to be left with meters. I always like to look at canceling the units to make sure that I'm doing things on the right track with the units. Like that's a good way to, like, if I forgot to square this, I would catch it with that, because if I didn't square this, I wouldn't have meters squared and seconds squared, and it wouldn't cancel right, and I wouldn't be left with meters when it canceled. And we know that what I should be left with is meters, because we're going to end up with a displacement. Okay, so to perform this calculation, I should have two significant figures in my final answer, because both of these have two significant figures, and we get 17 meters. I'm going to actually erase that and make it a little bit higher so I have plenty of room. 17 meters equals delta x. Okay, so I'm not done yet because I like to write a complete sentence. So the box will travel 17 meters. Okay, so make sure that I'm answering the question that was asked. How far will it travel before coming to a rest? The box will travel 17 meters. You could also say 17 meters before stopping to be more specific there. Okay, question 12. A 567 gram block is being pushed with a constant force of 4.11 newtons west. If it starts at rest and reaches a velocity of 12.0 meters per second west in 3.11 seconds, what is the coefficient of kinetic friction? Okay, so I have force west. I have a velocity that's west. The west is going to be my positive value. Going through my variables, immediately given mass. Whenever I see grams, I'm almost, and especially when I saw newtons in a later part of the problem, you pretty much automatically know you're going to need to convert it to kilograms. And so, like, as I'm reading this, I'm like, okay, this isn't 567 grams, it's 0.567 kilograms. Okay. The force is 4.11 newtons, and it's a force of pushing. Okay. It starts at rest. I see that word rest. So, and it's starting at rest. So velocity naught equals 0 meters per second. Reaches a velocity of 12.0 meters per second. So my final velocity is 12.0 and 3.11 seconds. So my time equals 3.11 seconds. And my unknown is going to be my coefficient of kinetic friction. So here, once again, I'm immediately thinking about, okay, what my last equation needs to be, because the only equation that has this coefficient of kinetic friction is that same one from earlier. My net force equals my force from pushing minus my force due to friction, and that includes kinetic friction in it, right? My coefficient of kinetic friction. So I have this, but I don't have this net force yet. And so again, I'm going to be working to figure out what that net force is first. Okay, so force, of course, is mass times acceleration. And we have the mass, but we don't have acceleration spelled out for us. And so what do we have that we can determine the acceleration from? And it's just our initial acceleration equation, right? So we have initial velocity, final velocity, and time. So that's where we're going to start. Acceleration equals our final velocity minus our initial velocity, so 12.0 meters per second. I'm not going to bother writing out that I'm subtracting 0, okay? So it's just going to be the final velocity with it kind of unstated, unsaid that, yeah, it's minus 0, minus the initial velocity, but because it's 0, I don't really need to write it. Now, your instructor may want you to do that, but I'm personally okay with that not happening. And divided by the total time, which is 3.11 seconds. Okay, and when I calculate all that out with 3 significant figures, it's going to be 3.86 meters per second squared is my acceleration. Okay, and so then my force is mass times acceleration, and so the mass is 0.567 kilograms, and my acceleration 3.86 meters per second squared. And so my force is, with 3 significant figures again in both of these, 2.19 newtons. Okay, so this is my net force. Okay, this is what actually happened. Okay, if you're measuring what is going on with this block. Okay, and so now I can plug that in here. So 2.19 newtons equals my force of pushing. I probably did not give myself enough room for all this. Okay, the minus my kinetic coefficient of friction is not, or coefficient of kinetic friction is an unknown, right? Times my mass, 0.567 kilograms, times my gravity, 9.81 meters per second squared. Okay, sorry, that's tiny. So let's calculate this out. I'm going to subtract the 4.11 newtons first. We're subtracting it here. And so I end up with negative 1.92 newtons equals my coefficient of kinetic friction with these multiply out and keeping it to 3 significant figures, 5.56 newtons. Okay, so kilograms times meters per second squared, we're at newtons. And now divide both sides by 5.56. Oh, and this should be negative, because that is negative there. and I get 0.345. Okay, no units because the newtons cancel. Okay, and coefficient of friction do not have units. So the coefficient of kinetic friction is 0.345. Okay, double check. That is the only question that was asked. What is the coefficient of kinetic friction? And that's what I have. No unit associated with it, no direction associated with it. Okay, question 13. An 891 gram model airplane is hung from a ceiling by a string, as shown in the picture on the right. If the airplane just hangs there, what is the tension on the string? What happens if the string cannot withstand that amount of tension? Okay, so we are going to have some vector quantity going on here. Okay, tension is going to be one direction and gravity is going to be another, right? And so we're saying, so tension is pulling up, okay? And so up in this case is going to be positive, okay? And gravity would be down, would be negative, okay? So whenever we have these tension problems, there are opposing forces, and so you do need to assign signs to those. So let's write out a variables. I have an 891 gram model airplane. I'm going to convert that to kilograms. Oh, there may be rare cases where you can just keep it as grams, but they're so rare, it's worth it to just automatically convert things to kilograms. Okay. So in this particular problem, we haven't really been given an equation that perfectly fits it. Okay. So it requires just a little bit of extra critical thinking because you haven't seen an example problem that looks like this that I know of, nor a comprehension check problem. Okay, but let's think about what the forces are. Okay, so tension, like I said a second ago, is a force that is pulling an object up. Okay, you might not be able to see it well, me drawing on this picture, right? And then the other force that is occurring is gravity, right? And so tension here, right? The other force is gravity, and that, of course, is pulling that object down. Now, there is actually no movement here, though, right? And so the net force, I got it right here, is actually 0, right? Because it's just sitting here. This plane is just sitting here. So our net force is 0. Let's try to put this into a problem. Okay, we have the net force, and that is the combination of this tension and the force due to gravity, right? So this net force is tension plus the force due to gravity is known as weight, right? Because it's the combination of mass times gravity. Okay, so we know that net force is 0, right? And we have tension that is our unknown, and then our weight is 0.891 kilograms times gravity. And that's negative. That's pulling it down, right? And so now I'm going to just move T over here and change the sign of this to just kind of make it look better, okay? So instead of negative T, I'm just changing the sign of this. So when I multiply these out and getting to 3 significant figures, I get 8.74 newtons. Okay, so because I knew my net force was 0, then basically the tension is the negative of the weight, right? And that is 8.74 newtons when I calculate that up. Okay, so there are 8.74 newtons of tension on the string. And the next part of the problem is what happens if the string cannot withstand that amount of tension. Okay, so the second part of that is if it cannot withstand that tension, then the force of gravity will win out, right? The string will break. And you could say, and the plane will fall. Okay. Question 14. This is not a calculation equation, so I'm just going to go through this one verbally. So suppose someone decides the string in the picture on the previous page is too visible. So the person wants to use thread to make it look less obvious. If thread cannot withstand the tension required to hold the plane, what can the person do to successfully hang the airplane by the thread? And so we know that if each piece of thread or each string or whatever holds a certain amount of tension, you can just add more pieces of thread or string to distribute the weight of that object among the different threads. So the person can use more than one piece of thread, and if there's more than one piece of thread, then they will share that load, and each piece of thread will have its own tension and distribute that weight equally. Okay. Question 15. A man is pulling a 154-gram crate with a rope at a constant velocity south. The tension in the rope is 305 newtons. What is the coefficient of kinetic friction between the crate and the floor? So I have velocity in south. We'll call south positive. And let's go through my variables. So my mass is 154 kilograms. My velocity is constant, but I'm not given any information on it other than that. So velocity, I'm just going to write what I have. Velocity is constant. the tension is 305 newtons. And what is unknown is the coefficient of kinetic friction between the crate and the floor. So for this problem, let's think about what that net force equation looks like. Okay, we have F net. So this tension is because of pulling, right? And so this is really, the tension is the same as the force of pulling here. Okay, I can call it T here, or you could call it F pull. Okay, but I'm gonna go ahead and put T, and you know, you can write equals F pull here to help you kind of visualize that. Okay, and plus my force due to friction, right? I know I'm gonna need this equation because I'm being asked about the kinetic friction coefficient. Now, I'm not given a lot more information, right? But if I have a constant velocity, what does that tell me about acceleration? Okay, this is a big hint that we were given. Okay, so constant velocity, this means that acceleration equals 0, right? It is traveling at a constant velocity. There's no acceleration. Well, then if we have force equals mass times acceleration, that means that force equals 0, right? And so that means that this net force that is what we are actually seeing happening, you know, if we are watching this crate being pulled, the net force is 0. So 0 equals the force due to tension, and I keep on putting a plus here, but minus that force due to friction. Okay, so now we're really going somewhere, right? We have we know we have everything we need. Okay, so I'm going to go ahead and move this over. I'm gonna put this here. So force due to friction equals T. And let's go ahead and plug everything in. All right, so we have our kinetic coefficient, or kinetic friction coefficient, 154 grams, or kilograms, my mass, and my acceleration due to gravity. So there is my F, right? And then my T is the 305 newtons was that tension. Okay. And so this calculates out to 1,510 newtons. Okay, the number's slightly different, but we need 3 significant figures. Okay, so that's what this is, rounded to 3 significant figures. Okay, divide both sides by that 1,510 newtons. And my kinetic coefficient, or kinetic friction coefficient, is 0.202. Okay, so the coefficient of kinetic friction is 0.202. It always feels weird writing these without any units, but you just got to remember that these coefficients don't have units, right? Because those newtons canceled. Okay, and just looking at significant figures, 305 had 3 significant figures, 1510 had 3 significant figures as well. The 0 was not significant. And so my answer has 3 significant figures. Okay, question 16. In the block and tackle system shown on the right, a load is attached to the lower hook. The load experiences a force of 112 newtons upward when a person pulls on the rope that is pointed out in the picture. With what force is the person pulling? Okay, so we have one person pulling here, and then a total force from all 3 of these pieces of rope that adds up to 112 newtons, because it's ultimately this object, this load, that is experiencing 112 newtons upward. Okay, and it's divided in between these 3. So 112 newtons, we're going to divide it by that factor of 3 pieces of rope that are actually pulling it, and we get 37.3 newtons. Okay, so this person here is actually pulling downward only 37.3 newtons, but because it's distributed in 3, or because it is applied into 3 different ropes, the total is 112 newtons, that a force that is being applied pulling the load upward. Okay, so the person, and I didn't do this, but force, vector quantity. Okay, so the person is pulling the rope with force of 37.3 newtons downward. Question 17. 2 spherical objects of the same mass are dropped. The first falls more quickly than the second. Which sphere is larger? So this is another one. I'm not going to write out anything because there are no calculations actually for the rest of this set of review questions. But I will go over it verbally. So the second sphere is larger, and that is because, given that they are the same mass, if it fell less quickly than the first object, then it means that it has a greater cross-sectional area, and therefore larger. For question 18, 2 objects that are identical in shape and size are dropped. The first has the higher terminal velocity, and which object has less mass? And so in this one, again, the second object must have less mass because it has less mass to overcome the air resistance, right? The greater the mass, the less affected an object is by air resistance. And so if it's falling more slowly, has a lower terminal velocity at the end, then it must have less mass because it's being more affected by the air resistance. Then finally, question 19, what property of air resistance causes falling objects to have a terminal velocity? And so for this one, that is the fact that air resistance increases with increasing speed. So the faster an object is falling, the more air resistance is actually being applied to it, and eventually that stops the acceleration. Falling objects, as the speed increases, air resistance increases, and therefore acceleration decreases, and eventually thus acceleration becomes zero. And so that ultimately is when we've hit the terminal velocity. The fastest that object will go, because no more acceleration can happen because of the amount of air resistance that is competing with gravity. Okay, so that is the end of this. Let me know if you have any questions.